In this lesson, we're going to be looking up close at Pythagoras' theorem and how it relates to triangle similarity, which we've already studied. From there, we're going to create a bridge to the study of triangle measurements, which is called trigonometry. To begin, we're going to consider this right triangle ABC with an altitude drawn CD. Recall that an altitude is a straight line drawn from the right angle of a triangle out to its opposite side, which in this case is a hypotenuse. The angle formed at this new point of intersection is 90 degrees. So we can say that line segment AB is perpendicular to line segment CD. Once the altitude is drawn, we form a total of 3 similar triangles. We have the original triangle ABC, and we have 2 smaller triangles, BCD, which I'm going to refer to as the red triangle, and CAD, which I'm going to call the blue triangle. I'm going to take a moment to construct breakout drawings of each of the 3 triangles separately, and I want to encourage you to practice doing the same. Specifically, I want to draw these triangles so that they are all arranged the same way on my paper with the right angle in the bottom right corner. Take care when constructing your red and blue triangles to ensure the corresponding sides are assigned correctly. Next, I want to turn my attention to labeling my side lengths and my angles. From the original figure, I'm given the right angles and the measure AC, which is 5 square roots of 2. I'm also given a 45-degree angle, A. Since I know the sum of the interior angles of a triangle will be 180 degrees, I can subtract to find the third angle, which will also be 45 degrees. That means all my triangles are isosceles right triangles because similar figures have congruent angle measures. I'm going to go ahead and label those angles in all 3 figures. Since I know that I have isosceles triangles, I can label additional side measures. In addition to having 2 congruent angles, isosceles triangles also have 2 congruent sides across from those congruent angles. That means in my original black triangle, BC is also 5 square roots of 2. Now looking to the red and blue triangles, I see they must be congruent triangles because they have the same angle measures and they have the same hypotenuse. So by angle side angle, they are not just similar triangles, but congruent triangles. Now I have enough information to find the area of the original triangle in black, ABC. The area will be half the product of the base and height. We haven't yet labeled the base or the height of the red or blue triangles. We'll need to use a special property of right triangles to find those values. Pythagoras' theorem relates the legs of a right triangle to its hypotenuse. Specifically, if we're given a right triangle, we can be assured that the sum of the squared sides, A and B, will equal the hypotenuse, which is C squared. We can flip this statement to its converse, which can be used to verify whether we do or do not have a right triangle. If this equation is true, then we definitely have a right triangle. Let's take a second look at those congruent red and blue triangles from above. We already know that this is a right triangle and that it is isosceles. This means in our equation, A and B are equal. Let's call them x. We also know the value of the hypotenuse, which means that we can use Pythagoras' theorem to solve for the legs of the triangle. Solving for x, we find that x squared equals 25, so x can be positive or negative 5. Since we're talking about the base or the height of a triangle, we'll go with the positive solution to that square root. At this point, it's possible to find the area of the red or blue triangle. The area is going to be 1/2 the product of the base and the height. Let's suppose we have triangle XYZ with an altitude drawn, XW. We create 2 similar triangles from that altitude. We have triangle WXZ in red and triangle WYX in blue. Now let's look to step 3 and complete the comparison. What triangle is similar to triangle XYZ allows us to compare the ratio of C to A, that's the hypotenuse to the height of the original triangle, to A to E? Well, we must be comparing it to the blue triangle, which is WYX. If we cross multiply to eliminate the fractions, we'll have A squared equals the product C times E. In step 4, we compare the triangle XYZ to triangle WXZ by showing that the ratio of the hypotenuse C to its base, B, is equivalent to the ratio of the hypotenuse B in the red triangle to its base, which is F. Once again, if we cross multiply to eliminate the fractions, we'll have that B squared is equal to the product of C times F. Now let's do a little bit of algebra. We can replace A squared with that product CE. So in A squared plus B squared, let's replace the A squared squared with CE. We can also replace b squared with the product CF. So let's replace b squared with c times f. Next, notice that both terms have a factor in common. They both have c in common, so let's factor out c. This leaves e plus f in the parentheses. Well, if we look back to our figure, e plus f makes the hypotenuse c of the original triangle, so I can replace the sum e plus f with c itself. Since c times c gives c squared, just like that, we have a squared plus b squared equals c squared. In our next example, we're going to verify that we have indeed formed a right triangle. It says Francis the rancher wants to verify that their new fence is constructed with posts perpendicular to the ground. The construction crew indicated that the fence crossbars are 10 feet across, but she would like us to verify that they have indeed constructed fence posts that are perpendicular to the ground. Let's check that for her. If they formed that right angle, this equation will be true. Let's see if it is. All right, next up we have a collection of right triangles referred to as Pythagorean triples. These triangles, like all right triangles, satisfy Pythagoras' theorem, but what makes these unique or special is the fact that the side lengths are all integers. Along the top row here, I have shown the first 4 Pythagorean triples, which are referred to as a 3, 4, 5 triangle, a 5, 12, 13 triangle, and so on. These are extremely common triangles, and it's merely helpful to be aware of them. This is one of the few patterns I suggest memorizing because it is really helpful for quickly solving missing side lengths or just simply identifying that you have right triangles. Along the second row, notice I've demonstrated how a 3, 4, 5 triangle might be scaled up. In the case of the triangle with sides 6, 8, and 10, we should recognize that this is just a 3, 4, 5 triangle dilated by a scale factor of 2. We saw the isosceles right triangle earlier in this video, but I want to take a few moments to point out the specific features of that triangle. First, and most importantly, there is only one isosceles right triangle with 2 congruent 45-degree angles on either side of a 90-degree angle. Opposite those congruent angles are 2 congruent sides, which are labeled here as S. Opposite the right angle, we have the hypotenuse, which always has the measurement S times the square root of 2. The ratio of A to B to C in an isosceles right triangle will always be x to x to x times the square root of 2. In this case, A and B refer to the legs, which are labeled here on the figure as S, or could be represented using the variable x, and C again represents the hypotenuse, which will always be the side lengths multiplied by the square root of 2. There's one more special right triangle we'll look at today, and that is the right triangle that results from drawing a perpendicular bisector through the vertex of an equilateral triangle out to the side opposite that vertex. In this case, our equilateral triangle will be split into 2 congruent triangles with angles of 30, 60, and 90 degrees. The shorter leg will be located across from the smaller angle, 30 degrees, which is shown here in blue and labeled S. The longer leg will be located across from the larger angle, 60 degrees, which is shown here in green and labeled S times the square root of 3. The hypotenuse, as always, will be located across from the right angle. It's labeled here as 2 times the shorter side S in gray. As with the isosceles right triangle, this pattern holds for all 30, 60, 90 degree right triangles. The longer leg is always the shorter leg times the square root of 3, and the hypotenuse is always twice the shorter leg. In the problem set that follows, you're asked to solve for the missing sides or hypotenuse for each of the given right triangles. You will need to use the Pythagorean theorem and the special right triangle pattern shown earlier in the video. I want to point out the process for this second triangle, which is an isosceles right triangle. We are given only the hypotenuse, and we need to solve from there for the side lengths. Well, we know that the hypotenuse 14 is equal to the side length times the square root of 2. To solve for the side S, we'll need to divide both sides of the equation by the square root of 2. Unfortunately, we'll need to simplify a little bit further because the simplified expression cannot have a radical in the denominator. You may recall this process is called rationalizing the denominator. To eliminate the radical denominator, I'm going to multiply by 1 in disguise. The square root of 2 divided by the square root of 2 is indeed 1. However, it allows us the opportunity to simplify that denominator. We'll have the square root of 2 times the square root of 2, which is the square root of 2 squared. That's just 2. In the numerator, multiplying across, I just have 14 times the square root of 2, which is 14 root 2. Now, I cannot divide a radical by a non-radical here. However, I can divide 14 by 2. That leaves the simplified expression 7 square roots of 2. Remember, the side lengths are equal because this is an isosceles right triangle. Please don't approximate this as a decimal, just use the simplified radical form here.